Okay, guys. So let me just say that this chapter has been, I think, harder than the others because there's lots of details, but it's well worth mastering it. And if you've understood this proof, well, that's really fantastic. So let's just do a quick recap, and then there's something specific I want to discuss now. So we've introduced this quantity, the wave function and normalization. And we know it's the probability with which a field will create a single particle state. So Z lies between 0 and 1, as any probability must. We were then also able to derive the key result as this second boxed formula, which is an exact result. D of p squared here, oh, there should also be a p squared. So d of p squared here is the Fourier transform of the two-point function. And that's what we're going to be discussing in this lecture. Now, this result, which is called the Lemon-Carlin spectral representation of the two-point function, is an exact result. All that we have used to prove it is Poincare invariance, so Lorentz invariance and translational invariance, and then unitarity. So it holds very generally in quantum field theory, and we're going to see that a big part of renormalization comes from understanding this two-point function. So the thing that I want to do now is I want to study this Fourier transform of the two-point function, d of p squared, and I want to think about it as an analytic function on the complex p squared plane. One of the other things I should say, so you know that Z is the probability with which create a single particle. Sigma of a squared is related to the probability with which our field creates a state with more than one particle, so two and other multi-particle states. Okay, so let's get down to business. What do I want to do? So I want to consider the complex p squared plane. So this is the complex p squared plane. And I want to think about d of p squared as an analytic function of p squared. And you can see d of p squared has got two terms. The first term shows us that there's a pole at p squared is equal to mp squared. So what we learn is, let's list that because that's an important point. We learn that the Fourier transform of the two-point function has a pole at the physical mass squared. So before we weren't sure where does the physical mass make an appearance in our formula, in our formulas, and now we found out it sets the position of the pole of the two-point function in the Fourier transform of the two-point function. Now we've got a second term sitting here. So let me just underline it in green. Look at the second term sitting here. So I want to study that second term next. And that's got an interesting structure. You can see we're integrating the a squared, and then we've got some numerator over p squared minus a squared plus I epsilon. So I'm going to think about a simple toy problem, which is going to be very useful to study. I want to study the following function. So let's study f of x is equal to, it's an integral from 0 to infinity, dz, and we've got z minus x, okay? And I'm going to start off just by asking two questions. So the first question is, what is the value of, now notice something. If I was doing this integral, and let's imagine that in fact x is greater than 0, so we'll make that assumption. If I was doing this integral, you see, integrating over z, I run into the pole. And you already know that when we get to the pole, we have to say, well, Do we go above the pole? Do we go below the pole? What do we do? So now I'm going to ask, what is the value of f of x plus I epsilon? So what do? We don't take a real value of x, we displace this real value slightly. If we displace this real value slightly, so where is the pole? Well, the pole is when z minus the argument of f is 0. So where's the position of the pole? Well, there is a pole at z minus x plus I epsilon is equal to 0. And that means we have a pole at z is equal to x plus I epsilon. Okay, so when we calculate the value of f, okay, so there is the integration contour, and this is the integration part. It's that blue line over there. And we have shifted the pole to sit just above the integration path, okay? Now, we, of course, let epsilon tend to 0, so a completely equivalent way to think about this is completely equivalent. I could also say, well, the pole sits at this position over here, but I go like this till I get to the pole, then I go around, and then I keep going. So both of these ways of thinking are perfectly valid, okay? So, good. I could also ask, what is the value of the f of x minus I epsilon? So in this case, where is the pole? The pole is at z minus x minus I epsilon is equal to 0. So that means that now the pole sits at z is equal to x minus I epsilon. So now the pole has got a very small negative imaginary piece, so it sits below the contour. And again, we're going to be able to think about this in two different ways. So the integration path now passes above the pole. So equivalently, we can think the integration path goes along there, and then when I get to the pole, I go slightly above, and then I keep going. Good. Okay, great. So now what I would like to do is the following. I want to study the value of f of x plus I epsilon minus f of x minus I epsilon. So what is this equal to? What integral should I do? Well, so here's the pole sitting over here. So here is the f of x plus I epsilon. Well, f of x plus I epsilon, that's the first picture that we had here. So we integrate away from the origin. When we get to the pole, we go slightly below it, and then we keep going. So that's how we integrate. And then I want to say minus the f of x minus I epsilon. And I want to take this minus sign together with the f of x minus I epsilon. Now we should have the second path that I've shown, but because it's negative, I should reverse the orientation of the path. So to get minus f of x minus I epsilon, I could integrate along this red path here. Okay. And add those two, okay? The minus sign has changed the orientation of the red path. So now I can just add those two. Now, what you can see is these flat portions of the path away from the pole, they actually cancel each other out. So that at the end of the day, what do I end up getting? I'll end up getting that piece of the contour together with that piece of the contour. Well, the residue theorem tells me exactly what this is. This is just going to be 2 pi I times the residue of the pole at z is equal to x. Now let's look at f of x at z is equal to x. The residue is just 1 because we've got a 1 over z minus x. So this is 2 pi I times by 1, which is just 2 pi I. So this difference of the function is 2 pi I. So what does that mean? What we have learned is this means that f of x is discontinuous across the positive real axis. So if I think about, so always we're integrating dz. So here I've always been drawing the complex z plane. So if I think about this function f of x, okay, how does it behave? Well, it would be discontinuous across this line. Sorry, I'm thinking here about the complex x plane. It would be discontinuous across this line. If I calculate the value of this function just above the real x-axis or just below the real x-axis, I get a different answer. So usually I have to put down I have to cut the complex plane. It's cut, indicating that the function is not continuous across here. Okay, so f of x would be an analytic function on the cut complex plane. And what this cut complex plane means is you can walk around, but you can't keep walking. You have to stop at the cut. You can come back again, then no problem. But you can't walk continuously through this point because the function is discontinuous across that line. And remember what our function look like? It was an integral dz, z minus x, an integral dz over a simple pole. Now look at our d of p squared. We've got an integral dA squared, and then we've got a simple pole in the denominator. So this is exactly the same form as what we just considered for f of x. Now let's just make a few comments. This function will be discontinuous in the complex p squared plane as soon as long as the residue is non-zero. But we know sigma of a squared, this is the probability with which you create a two-particle state. To create a two-particle state, what do we need? Well, sigma of p squared, for sigma of p squared to be non-zero, we need p squared to be greater than or equal to 2m squared. That's the minimum energy to create a two-particle state, which is 4m squared. So from 4, actually this should be m physical squared. So from 4mp squared on, sigma of a squared is non-zero, which means the residue of this term is non-zero. So we'll have a cut complex plane. So the d of p squared is no longer single valued. Okay. Sorry, let me just remove this. I want a bit more space here. So d of p squared as an analytic function is not single valued across this cut. Where is the physical value of d of p squared obtained? This region over here, the 2-point function, is physical in this region here. Okay. And it may happen in your theory that you get some bound states. If you've got bound states, they have an energy slightly less than a two-particle state. That's why they would be bound. So you may have some extra poles sitting here due to bound states. So these would be extra poles due to bound states. Okay. And these would genuinely be extra poles now at the mass squared of the bound state. And this statement about the analytic structure of the two-point function is an exact statement. All that you use to prove it is Lorentz and Poincaré invariance. So the Fourier transform, so let me now make an exact statement about the Fourier transform of the two-point function. It'll have a pole at the physical mass squared. It'll have additional poles at the mass squared of any bound states in the theory. And then starting from 4mp squared, there is a cut. Across the cut, the Green's function is not continuous. So if you evaluate the Fourier transform of the two-point function is not continuous. So evaluate the d of p squared just above the cut, or at the green dot, or just below the cut at the blue dot, and you'll get very different values. So that's why we need to cut the complex plane. What is the value of d of p squared for p squared real? It's the value that you'll get for the two-point function just above the cut. Good. These are exact statements about the structure of the two-point function, and we're now ready to get to the heart of this matter of renormalization.